Okay, so I'm going to set this. I have a string and I have a mass hanging from the string, and I'm just going to do this with it. The question I have for you is this in simple harmonic motion?
Yes. Yes.
Is it first? Is it in harmonic motion?
Yes. Yeah.
What's harmonic motion mean? Oscillates back and forth, and repeats. Is it in simple harmonic motion? In other words, what does it need to be in simple harmonic motion? What was simple again?
It has inertia and
Just
A balancing.
no. Simple harmonic motion was defined to be motion that's harmonic that is pure sinusoidal or cosine, right? Sinusoidal means sine or cosine. Means if you track this thing with the back and forth motion, would it trace a sine wave? Yes or no?
No. Why? How?
Would it?
What are you talking about?
If you had like
0 positive, 0 negative, 0 positive, 0 negative, 0 positive, 0 negative. Is that a sine
Yes.
or a cosine?
Yes.
Come on, Nathan.
We're talking about position.
It's not supposed to actually go in a circle.
Positive, 0 to negative 0.
If you plotted this thing's position as a function of time, would it be purely sinusoidal, or would there be some other goofiness going? It would be sinusoidal. Okay. So remember, sorry. One of these days, one of these years. All right. Remember that in order to be pure sinusoidal, in order to be truly simple harmonic motion, there have to be two things present. What are the two things? Inertia. Is there inertia? Yeah, because how come? Because it's got mass, right? There has to be inertia, but there also has to be what?
A linear restoring force.
A restoring force that is linear. So that's really the question, isn't it?
Yes.
When you displace it twice as far, is there twice as much force on it?
No.
No.
Wait, why?
Because
Is it tension?
What is the name of the force that's the acting as the restoring force? Gravity. Gravity. So if I pull this to 20 degrees, there's a certain amount of Fg. Is it Fg cosine or Fg sine? Pulling in the direction, restoring it.
Yeah.
Oh gosh, this is difficult.
Sine.
I think it's sine, isn't it?
Yeah.
Keep guessing.
Because if the angle is 0 here and 90 here, then it's maximum at 90 degrees, which would mean it would be sine, right?
Yeah.
All right, so it's mg sine, right? So if I pull it to 20 degrees, there's a certain amount of mg sine theta. If I pull it to 40 degrees, is there twice as much mg sine theta?
No, because the height's not double. Because sine 40 is not twice sine.
Exactly. Say that again.
Sine 40 is not 2 times sine 40.
Sine of 40 degrees is not twice as much as sine of 20 degrees. Do you see that? Okay, let's take it to the extreme case. If I pull it to sine of 90 degrees, is sine 180 twice as much? No, clearly not. Right? So this is not a linear restoring force, and therefore, it is not in simple harmonic motion. Did you know that? So all that stuff they did with you last year with pendulums, and they said, you know, simple harmonic motion, it was even in the simple harmonic motion unit, it's not actually simple harmonic motion. It's actually complex harmonic motion. And it's goofy. It's a little weird. It's like it lingers a little too long on either end, I think. Or maybe it's the other way around. Instead of being a sine, it's like a spiky sine. One or the other. It's either a flattened sine or a spiky sine wave. Does that make sense? If I say it that way, does that make sense?
Yeah, we understand.
Like a perfect sine wave would be a nice curve. A flattened sine would be lingering too long. Yeah.
Springs also complex too.
Is spring a complex? No. Springs are kx, right? Assuming it's a Yeah, assuming it's a linear spring, right? Then it's simple harmonic motion, linear restoring force. Good?
Yeah.
So pendulums aren't simple harmonic motion. However, are you aware of something called the small angle approximation for sine? Raise your hand if you've heard of this before. Angles less than like 10 degrees. All right, what's true? Use tangent instead.
They're really close. The tangent and sine values are really, really close.
Or if you're in radians, just use the arc length, the distance value. So theta equals sine theta pretty much. Did you know that? Theta equals sine theta. Pull out your calculators. Everybody pull out your calculators. What I want you to do is put your calculator in radian mode.
Oh, wait.
And do like a sine of, I don't know, what's a good angle? What's a good small radian angle? 0.1. Do sine of 0.1. See what you come up with.
Whoa.
What is it? 0.09999999999, right? Or something like that. Several nines. Do like a sine of 0.01. See what you get. 99999, right? So, if you have a small radian angle, the sine of the angle is pretty much equal to the amount of radians, which is really neat. Which means that if you had a small angle, you could just write the angle rather than sine of the angle. All right? We're going to use that idea. All right, so here we go. It's called the small angle approximation for sine. Okay, so let's say we had a pendulum. It had a length of L, and it was displaced an angle of theta. All right, and we'll call, let's see, I'm going to actually do this in terms of angle rather than in terms of distance or arc length. Are you guys okay with that? So the notes I'm about to give are going to be slightly different than the notes you have. You might actually want to write down this problem the way I'm about to do it rather than the way that's in the lecture notes. All right? Does everybody need a few seconds to pull out a pen and pencil? Or you can do it in Notability.
Oh.
All right. So here we go. I have a picture of a pendulum setup. We'll call the positive direction swinging to the right, the negative direction swinging to the left, and the zero mark is straight down. All right? Now, once again, we mentioned that a pendulum may or may not be in true simple harmonic motion. And the reason for that is the restoring force, the gravity force, is actually not linear, right? Because you double the angle, it doesn't actually get twice as strong. All right? So we've got to do a relationship between, well, actually, we're just going to write Newton's second law. All right. Newton's second law for angles is what? For a rotational version. Sum of torques I alpha, right? Okay, so we need to get the torque on the net torque on that hanging mass, right? Well, how many forces do you have? I say you have 2. You've got gravity pulling down and you've got tension going sideways, agree? But what is the restoring force in this situation? Well, it's not directly gravity, it's actually the component of gravity that's in the direction of motion, which would actually be this one right here, which is mg sine theta. Agree? Do you see how I get sine out of that? All right, this one would be mg sine theta. All right, so there's only one force that's restoring, so that is the only force that's providing the net torque. So if the force is mg sine theta and the length is L, what's the torque? L mg sine theta. What about theta? Oh wait, it's already 90 degrees, right? Because this angle right here is 90 degrees. Right? So we don't have to do LMG sine theta, sine of a different angle. Right? Okay. What's moment of inertia for this guy? mL squared times alpha. Good so far? All right, cool. So, we can cancel some stuff. M goes away. One of the L's goes away. And we're just left with G sine theta equals L alpha, which is a nice, simple equation, right? What I want to know is what is the equation for angle theta as a function of time? Do you see a problem here? You don't have time. I want to solve for theta as a function of time, but you don't have time. So acceleration, right. We can actually split acceleration up. What is angular acceleration with respect as
A over linear.
how does it relate to theta?
Theta over 2.
No. It's not constant. You can't use constant acceleration equations. What's the relationship between acceleration and position? It's dv over dt or d. It's the second derivative. Right? So we're going to actually write this as a second derivative. We're going to write g sine theta equals L d squared theta over dt squared. Got it? It's a second derivative relationship. And this is something called a second order differential equation. Second order differential equation. All right. It turns out that there is no way to just directly integrate this like you did in Calculus BC to find a solution. What you have to do is make a couple of assumptions and then memorize an answer. And that's going to drive you all crazy, I know. But that's just the way it is. Why? Are you familiar with the idea that if I write a if I write a random integral on the page, you won't be able to solve it? Why?
That's just how it is.
It's just how it is. Most integrals don't exist. Did you know that? In Calc BC, they teach you a bunch of integrals that do exist, but if I were to just write a random one on the page, you wouldn't be able to solve it because it doesn't have an answer. It doesn't have a solution. All right? Because in order to solve differential equations, it's the same issue. You got to solve them by integration, right? But if I were to draw a random differential equation on the page, same problem. The integral wouldn't exist. But there are certain differential equations for which there are solutions. And what I'm about to show you is one of them. So here it is.
How many are there?
How many? Okay, so next year you're gonna take a differential equations class. And in this class, they're going to teach you 3 or 4 major methods for solving differential equations, one of which you know already. It's called separation of variables, which is the most straightforward one. Then you're going to learn something like something called first-order linear equations, where you have to find an integrating factor. Then you're going to do second order, which I'm about to tell you. And then you're going to do a couple more special ones. And that's it. And then all the other ones, they're going to say, we don't know how to solve these. And or a solution doesn't exist for this. Yes?
The real, like, huge mathematical geniuses know how to solve it.
They've proved that a solution does not exist. Got it? Random integrals, mostly solutions don't exist. Yes?
Are they like regular questions, or are they not continuous?
They are differential equations. Do you know what that means? That. You have a derivative of something equal to the something. All right. So here we go. This one doesn't exist. This g sine theta equals L d squared theta over dt squared does not exist. However, I'm going to do something called the small angle approximation. What's that? If we displace this pendulum a very small angle, do you guys know what small means when you're talking angles? Less than about 10 degrees, or less than, how many radians is 10 degrees? I don't know. Like 1 radian is like 57 degrees, so 1/6 of a radian. So if you got 0.1 radians or less, then you can use this. So for small angles, if theta is small, which is less than approximately 10 degrees, or I don't know, 0.1 radians.
1.17.
Sure. It gets less and less accurate the bigger the angle is. You can say sine theta is equal to theta, approximately. All right? So anytime we see sine theta, what can we do? Change it to theta. So g times the angle, theta, equals L d squared theta over dt squared. Oops, I forgot something very important. What direction is this torque? It's negative. It's a negative torque, right? So it points backwards. So these all need, the left side all needs negative signs in front of it. Ah, if it was a positive torque, if it got pulled to here, what way would it be pushed? Up. So would it be in simple harmonic motion? Okay, so let's say you had the pendulum like this, and the torque pointed the other direction. What way would it fly? It would just keep on getting bigger. Oh, if you pull it to the other side? All right, the force needs to be in the opposite direction of the motion, right? Otherwise, it's not going to restore. A restoring force is negative. Macy, do you understand how that works on either side?
No, I did on that, so I had to probably get on the other side. Just...
Okay, good. Or not good, I don't know. All right, so what we want to do next is we want to massage this equation to get it in the following form. The second derivative of the variable equals a negative sign plus some constant times the original variable. If you have a differential equation that looks like this, where you have a second derivative, an equal sign, a negative sign, a constant, and the original variable, you can solve it. No, the negative sign is absolutely critical. Because remember, if this wasn't a negative sign, the thing would blow up. Right? It wouldn't be a restoring force. It would be an exacerbating force.
You know, like a negative, and then parentheses, the constant would be a negative.
No, this has to be some positive number. or else this thing will explode. All right? So, what is this constant here? It's d squared theta dt squared equals negative, and what's the constant? G over L. Wait a second. G over L times theta. Oh, this is interesting. G over L. Where have you heard that before with regard to a pendulum?
Oh.
Square root is
Yeah. Yes. Okay, so here's the deal. Yes, with the period and the time and the G over L thing. Right. Okay, it turns out if you have an equation of this form, the answer is, the general solution is angle as a function of time equals some constant times cosine or sine, depending on how you're feeling that day, omega t plus some other constant depending on your initial conditions. That is the general equation. Now, here's the cool part. Guess what omega is equal to? Square root of this. So this thing is omega squared. So omega squared is G over L. So what's omega? Square root of G over L. So whatever goes in front of the theta, or whatever goes in front of the, in between the negative sign and that variable, it's automatically going to be omega squared. Got it? Super, super cool. So now all I need to do, what?
What are the other blank units?
Oh, we need to fill in the other blanks. In order, remember, if you're doing a differential equation, in order to solve for the blanks, those would be the plus C's, right?
Yeah.
We'd need some initial conditions. So let's say if, let's see, initial conditions. Initial conditions, what do you want to do for an initial condition?
Degree of 3 degrees. Wait, you move it up on
Initial conditions, let's say theta at time 0 was equal to, I don't know, theta max. Does that sound good? Means at time 0 you held it up to the maximum positive value. Okay, can we solve it now? Remember, amplitude and phase constant. Whew. All right. So we need to solve for amplitude and we need to solve for phi naught. All right, so theta equals theta max cosine omega times 0. And if I'm using cosine, we know cosine is at a maximum, so I don't even need that phi naught. So what is A equal to? What's the amplitude of this thing? Did you follow the math I just did? Or was that just incredibly confusing?
Oh, I'm an idiot. Okay.
Yeah, initial conditions.
Yeah.
This is just 1. So A equals, oh, what's phi naught? That's your starting angle. So, yeah. Yeah,
How does the math support like getting rid of phi?
because I know that cosine is a maximum at 0.
What time is it?
At time theta, like the phase was like over here, so when that changed the phase, that changed the position it was at. So the cosine was like that.
Yeah, but I said you started like this.
Cosine starts at 1. It's at half.
Yeah. So, our specific solution, is that off the screen? Oops. Our specific solution is theta is a function of time, would therefore equal to theta max cosine omega t. Agree? But what's omega? Square root of g over L. So theta is a function of time equals the maximum angle, theta not max, times cosine square root of g over L times t. And that is your answer. All right? Which is kind of cool. What do you mean sine to cosine? I just assumed a cosine just because of this initial shape. Where are you looking? Oh, this sign went away. I cannot have a sign in my differential equation because if I do have a sign there, it's impossible to solve. It's not that I don't know how to solve it, it means there is no solution to the differential equation. The second derivative equals negative g sine theta. That doesn't exist. G over L sine theta. There is no solution to that differential equation. So you have to get rid of the sign right off the bat. There is a solution to this one. There is not a solution to this one. Got it? You have to use the small angle approximation in order to get an answer. You have to. If you don't do it on the AP test when this comes up, because it will, then you will be wrong. Got it? Now, there's this little thing in calculus or in differential equations where we actually probably ought to verify that the cosine root g over L times t is actually a solution to this differential equation. How would we do that? You'd have to plug in the stuff, right? We're going to take our specific solution and verify it. Here's how we do it. What's the second derivative of this? This root g over L squared, right?
Yeah.
Theta max g over L, oops, times cosine omega t, or I suppose root g over L times t.
And then a negative.
All right, agree?
With the negative up front.
With a negative. Oh, yeah, because it's a negative cosine.
Couldn't the first integral just be g over L sine theta? The second derivative of that would be negative g over L sine theta.
What's that?
Second derivative of g over L sine theta, wouldn't that be negative g over L sine theta?
Yeah.
So wouldn't that be the solution to the differential?
Oh.
What are you talking about to that differential equation? No.
With these.
I'll explain it because it would be sine of cosine. Okay, does that equal negative g over L sine theta, or g over L times theta? Does it? Yes or no? Does the second derivative equal negative g over L times theta? Yes or no? Well, theta, let's see, let's check it. Negative g over L times theta, but what was theta? Theta was theta max cosine omega t. So theta max cosine root g over L times t. Are they equal to each other? Yes! I have verified that the specific solution that I guessed would work does in fact work. Angular frequency, starting on the second page, it says memorize this. If you have a second order differential equation of the form d squared over x over dt squared equals negative a constant b times x, it has a solution that is simple harmonic. Specifically, the solution is going to be x of t equals something times cosine omega t. All right? Moreover, the b is actually omega squared. All right? Memorize that. All right? Sine also works. All right? So the example that we did is a pendulum with a small angle approximation. Omega was root g over L, right? So if omega is root g over L, what's the period of a pendulum? 2 pi root L over g. All right? And that's the real deal. All right? So, on what quantities does the period of the pendulum not depend? Mass. Did you know that if I hung two objects, a more massive one and a less massive one, they would both have the same period? Did you know that?
Yeah.
All right. All right? Because it's root L over G. All right. So we're going to stop there. Tomorrow we'll pick up with physical pendulums.